Good morning, everyone. My name is Sachin Singh, and today I will be presenting the paper on AI-driven optimization of 5G networks, predicting congestion and faults using machine learning techniques. Um, The talking point in today's presentation would be primarily we will be focusing on how artificial intelligence and machine learning can improve the performance and reliability of 5G networks. The research specifically targets two major challenges in modern telecom networks: the network congestion prediction, and the second one is fault detection and classification. In this work, I used random forest classifier for congestion prediction, support vector machine for fault classification. The goal of this research is to enable proactive and intelligent 5G network management. This study demonstrates how AI can reduce downtime, improve quality of service, and optimize network efficiency. This presentation is divided into six major sections. First, I will briefly discuss the abstract and overall problem statement. Then I will explain the introduction and the importance of AI in 5G networks. After that, I will cover related research, works, and existing approaches. Next, I will discuss the methodology, including data pre-processing and model development. And then I will present the results and performance evaluation of the proposed models. Finally, I will include the study and discuss future research directions. Now, in abstract, 5G networks generate massive amounts of traffic and require real-time decision making. Traditional network management approaches struggle to handle high traffic volumes, dynamic network demand, large-scale device connectivity. Now, to address these issues, I proposed a hybrid AI-based framework. The framework uses random forest for congestion prediction, support vector machine for fault detection. Several pre-processing techniques were applied to improve data quality, like, for example, missing value handling, normalization, one-hot encoding, outlier remover, feature selection. Now, the random forest model used traffic-related parameters such as download speed, upload speed, latency. Now, the SVM model focused on identifying different fault types using signal strength and error rate features. The proposed approach achieved very high prediction accuracy, especially with the random forest model reaching 96.5%. In this introduction, the my presentation points includes 5G technology is, we can say that it's transforming modern communication systems. It provides extremely high data speeds, ultra low latency, massive connectivity support. These capabilities enable applications such as IoT, Internet of Things, smart cities, autonomous vehicles, industrial automation. However, managing 5G networks is highly complex due to dynamic traffic behavior. Traditional rule-based systems are no longer sufficient for modern, excuse me, for modern telecom environments. Excuse me. AI and machine learning offer intelligent solutions for automated network management, resource optimization, real-time decision making. In this study, network traffic datasets were used to train predictive AI models. The main objective was to improve reliability and reduce operational cost through proactive prediction and fault detection. This slide summarizes previous research related to AI-driven 5G optimization. Researchers have explored different AI and machine learning techniques for traffic forecasting, for resource allocation, for congestion management, and for network slicing. The deep learning models, such as LSTM, GRU, federated learning, have shown promising results in traffic prediction. Now, the previous studies demonstrated that AI can improve quality of service, network efficiency, predictive maintenance. Some works focused on reinforcement, learning for intelligent network orchestration. At the same time, other studies explored anomaly detection and proactive monitoring systems. My research differs by combining primarily two things. One is random forest for congestion prediction, and second is the SVM for fault classification. The proposed framework provides both traffic analysis and device fault management together. Now, in this, basically, this slide explains the workflow of the proposed methodology. The first step was data collection from network traffic and communication systems. The collected data was then pre-processed to improve quality and consistency. Then the pre-processing included handling missing values, data normalization, includes including encoding categorical variables, removing outliers using z-score analysis. After pre-processing, feature selection was performed using recursive feature elimination. This helped identify the most important parameters affecting congestion and faults. Two machine learning models were developed, random forest for congestion prediction, support vector machine for fault classification. Um, the models were evaluated using accuracy, precision, recall, F1 score, and finally the AUC. Now, the system predicts congestion levels and identified networks using network faults for intelligent network management. Now let's talk about the results and discussion. This slide presents the performance metrics of both models. The random forest classifier achieved 96.5% accuracy, 95.8% precision, 96.3% percent recall, and 96% F1 score. The AUC value of 98% indicates excellent prediction capability. For fault classification, the SVM model achieved 94.5% accuracy, strong precision, and recall values. The results show that both models performed effectively for intelligent 5G management. Random forest slightly outperformed SVM overall. These results confirm that AI can significantly improve congestion prediction and fault identification in telecom networks. This is a little more explanation of what I just explained, that how the random forest model slightly outperformed SVM as well. Um, um, okay, so let's talk about more on this slide. The confusion matrix. Yep, here it is. Okay, so basically this slide shows the confusion matrix of both models. The confusion matrix helps evaluate classification performance in detail. For the random forest model, most congestion categories were correctly predicted. The model handled low and high congestion very effectively. Medium congestion categories showed a small amount of misclassification. For the SVM model, true positives appear along the diagonal of the matrix. This indicates accurate fault classification. For example, signal degradation cases were correctly identified with high accuracy, whereas only a few cases were incorrectly classified, demonstrating strong model reliability. Now, this figure four shows the distribution of different networks fault categories. Signal degradation represented the highest proportion of faults. Hardware issues were also a major contributor to network failures. Software failures represented a smaller percentage. The SVM model successfully differentiated between these fault types. Now, this figure 5 compares the performance of random forest and SVM models. Random forest achieved slightly better results across all evaluation matrices, which is accuracy, precision, recall, F1 score, and AUC. This demonstrates the stronger predictive capability of random forest for congestion prediction task. Now, um, let's talk about the ROC curve analysis. This slide represents the ROC curve comparison of RF and SVM models. ROC stands for Receiver Operating Characteristics Curve. It evaluates the trade-off between true positive rate and false positive rate. The closer the curve is to the top left corner, the better the model performance. The area under the curve, or AUC, represents overall prediction quality. Random forest achieved a slightly higher AUC than SVM. This indicates stronger classification and prediction performance. Overall, both models demonstrated high reliability for 5G network analysis. In conclusion, this research demonstrated the effectiveness of AI-driven optimization of 5G networks. The random forest model successfully predicted congestion with very high accuracy. The SVM model effectively classified different network fault categories. The proposed system supports early congestion detection, proactive maintenance, improved network reliability. AI-based monitoring can significantly enhance user experience in future telecom systems. However, the study had some limitations, and those are non-5G specific datasets, no real-time deployment analysis, limited deep learning implementation. This is why my future work may include real-world 5G datasets, deep learning models such as LSTM and transformers, federated learning, explainable AI techniques like SHAP and LIME, data balancing methods such as SMOT and GAN-based oversampling. This slide lists the references used in this research. This study was supported by recent research articles related to AI-driven telecom optimization, traffic prediction, machine learning in 5G networks, network orchestration, and resource management. Basically, these references helped build the theoretical foundation and validated the proposed methodology. Thank you everyone for your time and attention. I hope this presentation provided useful insights into AI-driven optimization for 5G networks. Thank you very much.